Okay, so today we would learn four different types of lab techniques, and those are listed here. So we are going to work with four different types of media, okay? And we'll do this as a pod, okay? And you guys would split the work. If we have four people on the pod, each person could just take one media and work on that, because basically we do the same thing but in different plates, okay? So this is what we do. It's kind of very simplified in here. So for each medium, we would have a plate, okay, and then we would take the bottom of the plate, is split into either four sections or three sections, and then we would have seven different species of bacteria that would have to inoculate on the plates. So you guys would just have to follow the instructions to know exactly which species would go for each medium. Okay, and we would do this from a broth. So then we would have to be careful because of the spills when we do this. Okay, but usually this is actually done very quick because the only thing we do is a straight line. It's not even like a zigzag, and then it makes much easier. So we already had enough experience so far to know what it means to streak a plate. So I'm not concerned that you guys wouldn't know how to do this. The only thing about each medium is to understand what we are learning from the results. Okay, so interpretation, it's going to be everything. So all the medium that we have today, they are selective and differential. So when we have a selective medium, because they don't have to be both, they can be either one, okay? It just happened that we have both aspects of the medium as being selective and differential, but you can only have selective media and only differential. So a selective medium, it means that we have ingredients on this medium that would not allow certain microbes to grow. And then therefore would just will promote the growth of others. Okay, so we are selecting which microbes we want to grow. So then we have the differential aspect of the medium, which is different. So this one, we have ingredients that will make us to see, like a visual result, see something different about the microbe. So we have what we call indicators and the differential ingredients in the medium that would make us to observe some type of color change, and then the color change would indicate something. Okay, so here, if the medium is only differential, we are not selecting what it can grow in here. Anything could grow, but then if it grows and the microbe is able to do something that we are trying to identify, then we can actually see as a visual indication of that result. It's very nice when we have media they're both selective and differential, because it helps us into the identification of unknown bacteria. Okay, so the first medium that we would inoculate, it's called Columbus CNA medium. And the CNA, it actually stands for the two antibiotics that we have in here, colistin and nalidixic acid, and then A is just for agar. So here on this medium, so the plate, you guys would take the plate and you'd see that the medium is actually red, very red. And that red is because there is blood on this medium, okay? So all plates that would work today, they are red, but then there are different shades of red, and they are red for different reasons. So this very first medium here, it's red because there's blood on it. And as I said, everything's going to be selective and differential. So if it's a selective medium, what are we trying to select in here? So this medium will not allow gram negatives to grow. You only allow the gram positives. Okay, so usually if we streak a plate, like a CNA plate in a clinical lab, we don't want to grow any gram negative, especially from the Enterobacteriaceae family or the Pseudomonas group, because they are not the ones in question here. So if the doctor believes that you might have a gram-positive infection, so the CNA medium might be an option, especially if they suspect that you might have a staph infection, or strep infection, or enterococcus infection. Okay, so this medium will only allow gram-positives, but those three genera here are the ones that usually will cause human diseases. They're going to be more common. So why do we want blood in the medium? Well, because there are certain microbes with virulence factors that can destroy the blood. So when they destroy the blood, we call that hemolysis. And we have three patterns of hemolysis. We have partial hemolysis or alpha hemolysis. We have complete hemolysis, complete destruction of the red blood cells, and that's beta. And then we have no hemolysis whatsoever. So it could be that the microbe is able to grow on the medium, but it will not destroy the red blood cells. They're there. Okay. So now let's talk about the ingredients. So there are a bunch of nutrients in here because, of course, we want the microbes to grow in here, just the gram-positives. And then the selective ingredients will be the two types of antibiotics in here because they will not allow the gram-negatives to grow. Okay, so they're very selective. And then the differential ingredient is going to be the sheep blood that we have. Okay, so the blood itself, it's not blocking the growth of any microbe. The only thing here is that if we have antibiotics that we will allow just the gram positives to grow, because those antibiotics will do nothing to the gram positives. Now you want to learn something else about the gram positives, because not all of them in here can do hemolysis. Okay, and if they do, they might do it in a different pattern. So that's why this is a differential ingredient. Okay, so again, this one will be very simple. This is what the CNA medium looks like. So the plate will be very red because of the blood on it. We would take the bottom of the plate, and of course we'll do everything aseptically. So we would split the bottom of the plate into 4 sections, and one section would be streaked with E. coli, and E. coli is a gram-negative. So this is just a negative control. We know we cannot grow in this medium, okay? And then we have another 3 different species of gram-positives, okay? So here we have 2 BSL-2 organisms, and means biosafety level 2. And those organisms, we have to be super careful when working with them in the lab, because if we had any spills from a broth, those are organisms that are known to cause human diseases. So that's why a spill would have to be taken care of really quick, okay? But the inoculation would be very simple. So we would streak, each section with the respective, bacteria, and then one of them would be a streptococcus species. We don't have to know exactly what strep species, because all of them kind of do the same thing. Then would be the enterococcus faecalis, and then would be staph aureus down here. Okay, so that would be that. Only that we need to do. Then we do the next medium, which would be the MSA agar plate or mannitol salt agar. Okay, so it's also selective differential. And now this medium, it's gonna do something even more selective. It has ingredients in here that will not allow the gram negatives to grow, and also most of the gram positives. Okay, so basically nothing can grow in here on this medium except staph and micrococcus species, which are gram positive. So that's why I'm saying, like, you can inhibit the growth of all gram negatives and basically all gram positives except staph and micrococcus. So micrococcus species, they're not known to cause human diseases. So the only reason we use an MSA plate from a clinical sample, it's because we are looking for staph species. Okay, so staph species are known to cause human diseases. And then if we see growth on the plate, it's because it is a staph species. But now we want to know more. Okay, so now it comes the differential aspect of the medium. If it grows, how do we know which staph species we have on the medium? Which one should we worry about? Well, the only one that really matters is staph aureus. Okay, so staph aureus is the one that causes several types of human diseases. and it has a lot of virulence factors, and we'll talk about that for the disease unit. So what happened is we have a differential ingredient here, and that's going to be the sugar called mannitol, and then Staph aureus is the only one that can ferment this type of sugar. Any other species of staph cannot do that. Okay, so we can see if there's fermentation or not, because right now the way how we used to grow the medium, to grow the bacteria in the media that we had, the media was just a regular medium. So if there was any fermentation going on, because there was fermentation going on, we couldn't tell. We just knew that certain species can ferment, but the regular medium that we use, either like on a slant or on a plate, there's no way you could tell that the bacteria is actually fermenting. Okay, so that's why when we have a differential medium, you have to add ingredients in here that will show you that there is fermentation. So the medium have several nutrient sources, okay? But the selective ingredient will be the salt. So I have mentioned this before, that we have staph epidermidis on our skin, and one thing that helps staph to be on our skin is because staph can tolerate high salt concentration that comes from our sweat. Okay, so here most species cannot tolerate that concentration of salt. So if you add salt on the medium, so now only staph species can grow. That's why it's our selective ingredient. Okay, then our differential ingredient again is going to be the sugar, because if we want to differentiate the staph aureus, because that's the only one that causes human diseases, against the other ones, we would see if there is fermentation. Well, but if there is fermentation of the mannitol, how do we see that? Because just fermenting, it's not enough. We want to see the fermentation. We need to have some type of a visual indication of that. So this plate would also be red, but it will be red because there is something called phenol red on it. And the phenol red, it's a pH indicator. And the phenol red is actually red at neutral pH. So all plates, all media that we start with, it's neutral pH. Okay. And then if there is fermentation, it means that the pH dropped, and it dropped like a lot. And then phenol red changed color depending on the pH that it's at. So if the bacteria that grows on the plate is Staph aureus, we would see phenol red turn into yellow. Okay, and that's how we know the fermentation was an indication of the color would be an indication of the fermentation of mannitol. So this plate would be, this type of color again. So it's a different shade of red, okay? But then we would take the bottom of the plate. We would just split into 3 sections. And then we would try 2 different species of staph, just to know that we can differentiate Staph aureus from another staph. And it happens to be Staph epidermidis. And then we would have E. coli again as our control, because E. coli, it's a gram-negative, and it should not grow on this medium. Like any other cells, any other types of bacteria could not grow on this medium except staph. Okay, so then that's all we'll do for this medium. Okay, then we'll follow with the next medium, which would be the McConkey agar. And this one again is going to be selective differential. And now we are changing sides here. We are not interested in the gram positives anymore. So there will be ingredients on this medium that will not allow the gram positives to grow, but instead would favor or promote the growth of the gram negatives. Okay, and the Enterobacteriaceae family have a lot of species of bacteria that can cause human diseases. A lot of them are opportunistic because they live in our intestines, and then if they get a chance, they will become opportunistic and cause disease or some type of condition. And here we have some examples of Salmonella, E. coli, Klebsiella, Shigella, but those are just some examples of species that we can test positive for a McConkey agar, and all this type of media is just a start point to get to the diagnosis. Okay, not it's going to be just one single medium. You have to run more than one test to know if you actually know what you have. So there'll be a bunch of ingredients in here, of course. There'll be the nutrient sources, and then what is gonna inhibit the growth of all gram-positives would be biosalts and crystal violet, the same of crystal violet that we use for gram stain. Okay, so the presence of those will not allow the gram-positives to grow. But the gram-negatives, they don't care. And if you think about it, it makes sense because biosalts are released in the very first part of the duodenum, and that's the in our small intestine, and that's just to make sure that the fat that we ingest in our food it's going to be dissolved and broken down, and all the gram negatives that we have from Enterobacteriaceae family, they are there, so they don't care about the presence of biosalts. So that's why this would be just inhibitory for gram positives. So now for the differential ingredient, we have lactose, okay? And why do we have lactose instead of glucose? Well, glucose is the most abundant sugar that we know, and most bacteria can use glucose. Well, the goal in here, it's not to just have glucose for all of them to use. We want to use a sugar that could differentiate them, so it can just split them apart. So from all those different types of coliforms or Enterobacteriaceae members, some of them can ferment lactose, but some of them cannot. Okay, so here the goal is to differentiate lactose non-fermenters versus lactose fermenters. Because if we had glucose, then all of them would ferment glucose. There was no way to differentiate anything. So we are trying to learn something else about the gram negatives that can grow in here. So this plate would also be red, not because of phenol red, not because of blood, but because of neutral red. So neutral red, it's another pH indicator. It's also red at neutral pH, but then if there is fermentation of that sugar, whatever sugar in this case is lactose, neutral red will turn pink. So the medium where you see the growth of the bacteria, if there's fermentation of the sugar, we would see the medium turning pink. So pink, it's very different from red. Okay, we could definitely tell the difference. So for this plate, we can see here, the McConkey agar plate would take the bottom of the plate, streak in 3 sections, and then we would do inoculation with Proteus mirabilis, E. coli, and Staph epidermidis. So Proteus mirabilis and E. coli, they're both gram negative, so it means they would grow on the plate, easily, but not staph, because staph is a gram positive. So this is just a control, just to make sure the medium would give the correct results, because staph is not supposed to grow in here. But that's all you would do, just a straight line for each of those pieces on the plate. Then we would go to the next and final medium that we would inoculate, called EMB, which is the eosine methylene blue agar. Okay, so this medium, it's the darkest red plate that would have. Okay, it's also selective and differential, and this medium, it's similar to the McConkey because it only allows the gram negatives to grow. Okay, so we're not interested in the gram positives. We would have selective and indicator ingredients in here, which would be the eosine Y methylene blue on it. They will not allow the gram positives to grow, but they would also react with certain bacteria that ferment the sugars that we have in here, and then they would give us a color indication of that. So that's why those ingredients they play 2 roles in here. Okay, but what are the sugars that we have in here? So we're going to have lactose and sucrose, because again, most coliforms, most bacteria that live in our intestines, and most of the Enterobacteriaceae members, they can ferment glucose. So here we have lactose and sucrose, which are not simple sugars, not like glucose. So if the bacteria grows on the plate, it means they're gram negatives. So now it's the point, are they able to ferment the sugars? Well, that's another story. If they can do that, we would see a color change, okay? And then the color change may vary from like dark purple to kind of pinkish. So the more fermentation we see, the darker the plate turns, the growth. And then that's how we can kind of differentiate and identify coliforms. So this is representing what the EMB plate looks like. It's a very dark red plate. And then we will take the bottom of the plate, split into 4 sections, and then we would inoculate Proteus mirabilis, E. coli, and then they're both, gram negatives as well, so they would grow on the plate. And then we'd have Staph epidermidis, which is a gram positive, so it will not grow, but we need to have a control. And then we have Enterobacter aerogenes, which is also a gram negative, so it would grow in here. So then again, that's all you do, just a strict line for each species. And then just to make sure that all the 7 different species of bacteria that we are using, that we would be using that night, we need to make sure they're all healthy. So we will take 2 regular agar plates, as we already have done so many times before, and then we would streak all of them, all the species, into those nutrient agar plates, just to make sure that the bacteria is healthy and it would grow without any pressure of selection here, because there's no ingredients blocking their growth, so they would grow just fine. And then we could just, when we see the control plates, then we can look at the results. Okay, so at the end, this is what you guys would have. So each pod would have 1 plate for each medium, because we have 4 selected and differential medium here, and then you'd have 2 control plates as well. So you'd have to just incubate all those 6 plates, and then 2 days later we would see the results. Okay, so let me walk you through what the results are. So one thing that we would have to discuss before we look at the result is specificity and sensitivity, because on your data sheets you're going to have to answer questions related to that. Okay, so when we talked about specificity, there's a direct relationship with the selective ingredients, because here when we add something that will favor the growth of certain microbes and will not let others to grow, that it makes it very specific to, it gives specificity to the medium. If you forget, let's say if you make a medium from scratch, and then you forgot to add selected ingredients, anything that grows on that medium, you're going to think it's positive until you realize that you forgot to add the selective ingredients. Well, now it's probably a false positive. It's false because it shouldn't be growing there, because you forgot to actually select it. Okay, so now when we think about sensitivity, it's different. It's not about selective ingredients anymore. This is about the indicators and the differential ingredients, because adding the differential ingredient, it's one thing. Let's say you have a sugar there, but then if the microbe ferments the sugar, well, great, but how do you see that? Well, you need the indicator. Okay, so the two kind of goes along, because if you forget one of the two or both, it doesn't matter. The medium would not be able to sense a change in the pH. So if the pH dropped or not, you can't tell, because you forgot either the differential ingredient, or you forgot the indicator, or you forgot both. So even if the bacteria is doing something, you can't tell because you can't see it. Okay, so then let's say if you look at the results, you'd say, well, the result is negative because I didn't see a change. Well, but if you realize you forgot the ingredient, well, now it's a false negative, because you just selected, you didn't, first of all, you didn't put the ingredients there to have a result, to actually see it. Okay, so the specificity has nothing to do with sensitivity. Okay, where once you select what you can grow there, it's one thing. Now whatever grows on the medium, because now you're not selecting, so whatever grows on the medium, the only thing you're interested in is to have some type of indicator that shows you what the result means, because if there's fermentation or not, it has to be some type of visual indicator for that. Okay, so the first step would be looking at the control plates, making sure all the bacteria can grow, and we always get great growth. We don't expect to have the same growth for all of them because they're different species, okay, but they would be a very thick growth for each of them. Okay, and then we would go straight into the results. We would look at the CNA medium first. Okay, and because we would only expect gram positives to grow, especially staph, strep, enterococcus, we would see growth for all of the 3, but we wouldn't see any growth for E. coli because, of course, E. coli is a gram-negative. It's not allowed to grow on this medium. But the next step for us would be looking at hemolysis. Okay, so we want to see which of the three species were able to actually destroy the red blood cells. And for this one, because we have to perhaps even open the plates, we would need to go to the biosafe cabinet in the back of the room, and then we would have some type of light box in there that we could look through the light like this to see the hemolysis pattern. Okay, so if we have like beta hemolysis, complete destruction of the red blood cells, the redness of the media would be gone because the red blood cells are destroyed. So we would see this clearing all over the plate. It's beautiful when we can actually see this. So then that's how we know it's beta. Okay, but then if we get like a partial hemolysis, when we look against the light, the growth looks greenish because the red blood cells are not completely destroyed yet. Okay, so then that's how we know. And then if a callus can grow on the plate, but then the growth itself, if we look against the light, there will be nothing. There's no difference in the background because the blood's still there. It did not destroy it. Okay, so the blood, it's not blocking the growth of anything here. It's not inhibitory. The blood in here is just to show if there's a pattern of destruction. Okay, so this result usually is very straightforward for what we do. Then we would look at the MSA plate. Okay, so again, the MSA plate is highly specific for staph species because micrococcus can grow in here, but it doesn't matter because they're not supposed to cause any human disease anyways. So we want to look at the staph species. Okay, so now for the staph species, we would have two that we're looking at, Staph aureus and Staph epidermidis, okay? And then E. coli would be our control. So E. coli doesn't grow in here or grows very poorly, okay? So we want to see the growth of Staph aureus and Staph epidermidis, and then we want to try to differentiate which one can ferment mannitol. So we know that the only one that can do that is Staph aureus. So this is a very straightforward result. You see this beautiful yellow growth for Staph aureus, and then there's no difference in the background of Staph epidermidis. Okay, so that's how we can differentiate both. Then we would look at the McConkey result. Okay, the McConkey now it's promoting the growth of gram-negatives. Okay, and we had a control here, which is a Staph epidermidis. So Staph epidermidis would not grow at all on this plate. Okay, but then we have P. mirabilis, and then we have E. coli, and they can both grow in here. Okay, but now what's the difference between them? Because growing here just showed that they're gram-negatives. What else can they do? Well, now we're going to look at the fermentation of lactose, because that's the sugar that's present on this medium. So for E. coli, it is a coliform. So when we see a lot of fermentation in here, the pH indicator would turn pink. So you see this beautiful pink color around all around the growth of E. coli, and that's how we know that based on the interpretation, if it turns pink, we would see that would be probably a coliform. So that's why you need more than one test to prove that you have a certain species. Okay, but since we're doing this from pure culture, that's what we would expect. Okay, now for P. mirabilis, there'll be no fermentation whatsoever. So basically the color of the growth, it wouldn't be different from the background. Okay, and then if you look on your lab manual, it may say colorless, and that's not true, because there's no color. It's just because it's not pink or it's not red anymore. It's just not that's how we just call colorless. Okay, and that means there's no fermentation, and it means that it's not a coliform. Okay, so that's the interpretation of this. Then finally, we would look at the EMB plate results, and this one, because it only allows gram-negatives to grow, Staph epidermidis again would be our control, and then you would see no growth at all for SE down here, but then you would see growth for the other three species that we tried. But you can see they do not look the same, okay? Because, growing in the medium means it's a gram negative. So now we want to learn something else about them because we have two sugars in here. We have lactose and sucrose. So E. coli is the one that gives us the beautiful result because that's the one that's a coliform and it's able to ferment both types of sugar, lactose and sucrose. The more fermentation we see, the more color change we see as well. So we are actually going to identify this very green metallic sheen on the surface of E. coli, and we have to kind of turn against the light to see that as well. But this type of indication would show you that this is a bacteria that it's likely a coliform because it can ferment both types of sugar, okay? And for aerogenes, we would see more like a pink, sometimes kind of dark purple growth. Here in this plate, it's just showing pink, but sometimes we see purple. And then sometimes even the E. coli shows purple, but it does not, you don't see metallic sheen on this one. We only see metallic sheen for E. coli. That's how we can tell, we can tell them apart, okay? And for this one, we can, based on the identification, the interpretation table that you guys have on your lab manual, we would say that there is fermentation going on, but that's not too much. So there is fermentation of lactose, but with little acid production. Okay, so only lactose would likely be fermented, not both sugars. Okay, and that's why we don't see a lot of color change. And then for P. mirabilis, this one would grow, of course, because it's a gram negative, but it does not ferment anything, okay? And because it doesn't ferment anything, when we look against the light, we wouldn't see like a huge color change from the background, and it would just interpret as colorless. But it's not because there's no color, it's just because it's not dark purple or kind of towards dark pink. So that's why we know the difference, okay? And then that's how we know for the interpretation of being colorless, that would mean that this is not a coliform. So it's not an infection from this one, okay? So now we are not doing, you guys are not turning in your data sheets from your lab manual, okay? So from now on, and I'm not going to explain this again, this is the only time I'm going to explain this. So we are going to provide electronic data sheets. And this I have just an example of my student view of Canvas. So if you go into every module for all the types of labs that we have to do, you guys know there's a module for every lecture. And then at the very end, if you scroll down, if you keep scrolling down, you're gonna see every lab that we have. And then if you go here for this lab, that's the selective medium, you're gonna find the pre-lab questions that I think most of you already answered this. And then this is where you take, the quiz for the same question that you have over here. And then now this is where you're going to find the electronic data sheet. Okay, so it's already posted in there. It's already available. And then you also going to have more results in here, in addition of having this PowerPoint presentation. So I will post this PowerPoint somewhere in here. Okay, so it's not showing here yet because I'm just recording this. But I'm going to post this PowerPoint under here as well, so then you can have access to it. You don't have to go back and forth between the video, so you don't have to actually worry about this. But the PowerPoint slides that I'm talking right now through them and this video will be under here in selective medium, and this is going to be the same thing for every medium that we're going to do inoculation, okay, for every lab. I'm going to have a video and I'm going to have the electronic data sheets, and then you guys are going to have a link to submit the electronic data sheets, okay? So make sure that you do this in Canvas. If you're not sure how to do something, just let me know. And for this part that says lab result pictures, this is what we are providing as well. So it's very hard to see the control plates over here, but this is just showing how much growth we would have on the control plates. And this is just another way to see, the results, the same results that I showed you guys already. And for this one, you can kind of see aerogenes and E. coli. The metallic sheen, when you actually see the plate, it only looks more realistic for E. coli. We don't see it. This is more like purplish when we actually look at the results. But this is just another way to see it, okay? In addition of having the results that I showed you on the PowerPoint slides as well. So you can based on this to answer your questions as well. In here, when you click on the electronic data sheet, and this is just showing you an example of what's going to look like for this selective medium, but you're going to have the same thing every time that we have a different lab, okay? So I'm not going to walk you through all of this again, but I'm just trying to explain now how you find electronic data sheets for every lab that we have, from now on. And I'm always going to post the PowerPoint that I'm explaining, because usually I don't provide the PowerPoints for lab, but just to make it a little bit easier for you so you don't have to go back into this video again to watch. And then you can just look at the PowerPoint slide and find the information. Okay, and that's all for this lab. This lab is super fun. I wish we could have done it, but I think you guys know enough to understand what we would do. Okay, so I'll see you guys on the next lecture and lab.